So in this video, we'll be talking about clustering and how it works compared to principal components analysis and when you might use this to attempt to reduce the dimension of your data. So clustering works a little differently than principal components. However, many people still think of it as a dimension reduction technique. So clustering is used to find a set of subgroups or clusters in a data set. Essentially, what we're trying to do when we cluster is find classifications that weren't actually represented in the data. So clustering is like a classification problem in that sense. However, we just don't know what the right classes actually are. So we're trying to look for groups of similar observations. So to cluster, we need to have an idea of what makes the observations similar and what makes them different. In most cases, this becomes a Euclidean distance sort of measurement. We also need a good way to decide how many clusters there should be. This is trickier. There are some similarities between clustering and principal components, namely both are unsupervised, both attempt to simplify the data. The major difference is what we're trying to simplify. So PCA finds that low dimensional representation, so we're simplifying across the variables or the columns of the data set. When we cluster, we try to find similar subgroups among the observations. So clustering really should be used to simplify across the rows or the observations. There are two major classes of approaches for clustering, k-means clustering and hierarchical clustering. So we'll talk about both of those in this video and how they work. So let's start with k-means clustering. In k-means clustering, we partition a data set into a pre-specified number of k distinct clusters. We need a way to decide how many clusters there are and where we're going to place those clusters. Now, there are some interesting quirks of k-means clustering, and you'll actually work through this with a very small toy data set. I want to show you another toy data set. This data set is called the Smiley data set. It comes from the ML Bench library. There's actually a function in that library to simulate data that looks like this beautiful smiley face. So we've got two eyes, a triangle nose, and then a mouth in our smiley. So what I want to show you here is how k-means clustering performs using the default options with different levels of k. Now looking at k equals 2, for example, so we're going to collect the data up into two groups. Looks like the eyes, nose, and eyes and nose primarily make one cluster, the mouth makes another. As we increase the number of clusters, we're seeing more subgroupings. However, they don't really fall into sort of the clear face shape until k equals 5 or 6. K equals 4 doesn't actually identify here, nose, and mouth. The eye and the nose are put together, and then the mouth is split into two different clusters with this run. So kind of a fun result. If we tried this again, it might look a little different. So here's the basic algorithm. We're going to let C1 through CK represent different sets containing the indices of the observations in each cluster. So in other words, we're going to take each observation and assign it to one of the K clusters. Further, we're going to force each of these clusters to be disjoint or non-overlapping. In other words, the intercept of cluster K and cluster K prime is the empty set or the null set. A good clustering, so one that we want, is one where all of the points inside the cluster are as similar as possible. So we want to keep similar observations close together in the same cluster. Observations that are far apart or dissimilar, we want to put in different clusters. We'll do this by trying to minimize the variation within each of the clusters. So our optimal clustering will minimize this. We'll minimize the sum of our measures of variation. We'll call those W. So W is a measure of the amount the observations within each cluster differ. How do we define this W? Well, there's a lot of options, one being Euclidean distance. So within each cluster, we'll take the distance between 2 points, we'll sum that up for all points inside the cluster, and then we'll divide by the number of points in each cluster. So here's how this will work in practice. We'll randomly assign a number from 1 to k to each of the observations. These are the initial cluster assignments. These clusters don't have to have the same number of observations. In fact, there's no guarantee that they will have the same number of observations. So we don't need to assign equal numbers to these initial clusters. So until the cluster assignments are stable, or in other words, stop changing, here's what we'll do. For each of the k clusters, we'll compute the center cluster, or the cluster centroid, so we'll find the middle point in the cluster. We'll then reassign each observation to the cluster whose centroid is closest, and repeat, and we'll keep iterating through this process until our assignments don't change. Now, k-means clustering finds a local solution, so this isn't a global assignment. What that means is that depending on where we put those initial random clusters, the results are going to change. So here you see clustering on the smiley. This is the first run. Again, it looks a little bit different from the one that we did previously. Here's another. So notice how some of these cluster assignments change. I think k equals 4 is a really good place to see how these groupings are changing. K equals 5 looks pretty different as well. Notice that the numbers are changing. The numbers in each cluster are rather arbitrary. So cluster 1 means nothing. We could call it cluster epsilon 2 for all we cared. Let's look at another data set. So this is a set of simulated points according to a spiral. And even for this spiral, the clusters are changing. Now the basic shapes of the clusters aren't changing, but the identifying numbers of the clusters and where we're dropping those points or those cut points on the pie also appear to be changing. So let's try this with some real data. So I'm going to pull the college data set, just like we used in the previous video, and I'm going to try to figure out what colleges are similar. I'm going to split this data up into 2 subgroups before I do this. I'm going to split it into public versus private. The only reason I've chosen to do that is because we have 700 plus colleges and universities, and I want to be able to see what's happening a little bit better. So we'll create a public and private data set. Here, I'm going to use base notation because I want to keep the row names. When you're doing clustering, it's very important, if you can, to name the rows. So here I'm naming the rows of my public data set and my private data set according to the college names, and we'll see why in just a minute. The function to create this k-means clustering model is k-means. There's 2 inputs here. We need the data set, so we'll do the public universities first, and then the number of clusters, k. So centers equal 4, we'll use 4 clusters. Once I fit this, we get the names, or we can look at what's actually recorded in this. We have the cluster, we have the centers for each of the clusters, we have tot SS, this is total sums of squares. Within SS, within each cluster, sums of squares. And then we can look at each of these clusters to see where they're being assigned. So for example, Arkansas Tech University and Bemidji State University have both been put in cluster 1. They're considered to be similar. That factoextra library, again, is going to be really helpful for us to visualize these clusters. So here I'm using a function called fvisCluster. There's 2 inputs that need to be written in a list. So the data is the public data set. The cluster is the cluster from the model applied to this. Here you see clusters 1, 2, 3, and 4. So we have some sort of vertical separation here. Taking a look at the x and y axis. This isn't plotted on any of those input variables. This is actually plotted against the principal components. So usually when you look at the principal components in conjunction with the clustering results, you could see the separation a little bit better, especially for high dimensional data sets. So that's why I like this particular visualization. If I increase my number of clusters, we'll now just take these groups and split them up a bit more. So all of the points are in the same place. The groupings have changed. One thing to keep in mind, with large data sets, it can be really tricky to actually visualize what's happening in each of these clusters. This looks like a ggplot2 plot, and it is. So that means that I can layer additional features to this ggplot2 plot using the plus sign. So here I've added facet wraps, so I'm actually splitting this up by each cluster now. Scales are free. And then I'm removing the guides. This just takes those legends away so they're not repeated 7 times. Here we see something kind of interesting. Cluster 3 only has 1 university. So it looks like Rutgers, which is the State University of New Jersey, is pretty different than the rest of these colleges. Now it's difficult to tell without looking at a list, but here Cluster 4 looks like it's got University of Michigan, University of California, UW-Madison, Michigan State. So these look like they might be the land-grant major institutions. Same exercise for private colleges. The grouping looks pretty similar in terms of first dimension, second dimension for groups like this. Again, it's pretty difficult to tell what these are actually representing or how these universities are being grouped just because we're not really seeing all we could see. So one other approach to clustering is a technique called hierarchical clustering. So when we cluster according to a hierarchy, we're combining observations using a pairwise approach. The advantage of hierarchical clustering is that we don't have a pre-specified number of clusters, k. Disadvantage, this takes a little longer to do. So the clusters are built using a dendrogram or a tree diagram. I'm going to start with just a subset of observations from the smiley so we can see how this works, and then talk about how we would determine a set of clusters from this. So the first step to doing hierarchical clustering is to calculate a distance. So here I'm just going to take the first 50 observations from my toy smiley dataset. I will calculate the distance using the dist function. Here I'm using Euclidean distance, and I'll save that as an object in R. I'll use the hclust function to calculate the hierarchical clustering, and then I'm going to plot this. This option here in the plot, CEX equals 0.5, that is shifting the text down half a unit so that I can see the labels here. So each of these labels indicates which row of the data that we're looking at. That's why row names are really useful to have when we're clustering. What we'll do is look for successive pairs of observations that are close together. Each pair of observations that is closest will become clustered or grouped. Once we've clustered or grouped 2 observations, we'll calculate their centroid and then use that as our next distancing. To see what these clusters look like, we can draw rectangles on top of the diagram. So if I want to add a rectangle to my hierarchical clustering, one thing to note is that in R, this is an additional function that's being applied specifically to the plot. So these always have to be ran together for these rectangles to draw. So I'll draw rectangles on top of my hierarchical clustering model. I'll draw 3. Border equals 2 to 4. Colors in R can be called according to integers. So here I'm calling color number 2, which is red, color number 3, which is green, color number 4, which is blue. Color 1 is actually a black rectangle, so that's why I've chosen to omit it here. So looking at our 3 clusters, it looks like we've got a cluster of observations here, 1 here, and then 1 here. If we want to use more clusters, say 4, we'll just look for 4 of these drop down. So here are the 4 clusters. 1 and 2 look like they've stayed the same. Going from 3 clusters to 4 clusters, we've split this big blue rectangle. As we go down to 7 clusters, we get more and more splits. So one advantage of, say, hierarchical clustering is that more clusters simply split existing clusters. We can plot these clusters as well. Here I'm using a function called CU tree, so I'm going to cut my cluster tree, you can think of it like that, into 4 clusters. I'll then add those to my smiley data and create a plot so we can see where those 4 clusters fall. Visually, we've got a group of observations here, a group here, group here, group here. This fviz cluster function will also add the centroids. So these plus square, diamond, triangle, those are actually the center points of the clusters. So here's what it looks like when we apply this to the smiley data set. So the full data set with just 4 clusters. We kind of have the smiley shape going on, but there's some weirdness with cluster 3. All right, algorithmically, we start hierarchical clustering with n observations and some measure of the pairwise dissimilarities or the pairwise similarities. We examine all intercluster similarities. We identify the pair that are least dissimilar. So the book uses least dissimilar. We look for observations that are similar or close together. We combine those into clusters and then we keep going. One way that we can define this dissimilarity between 2 clusters, once they've got multiple observations, is the linkage. So the linkage measures relationships or dissimilarity between 2 groups. There's 4 commonly used options for linkage. We can use complete linkage, where we use the maximum between all observations in cluster A, all observations in cluster B. Single linkage uses the minimum. Average linkage uses the average dissimilarity. Centroid uses the center dissimilarity. All of these dissimilarity measurements you can really think of as just distance measurements between points. So let's say we want to compare the clustering result using multiple linkage methods. So I'm going to use the first 50 observations of the smiley to do this. I'll specify 2 methods. I'll do hierarchical clustering with complete linkage and with single linkage. Here's what this looks like with complete linkage. Here's what this looks like with single linkage. So if you notice, these clusters look pretty different. Complete linkage results in 4 more evenly spread sizes of clusters, whereas single linkage results in 2 observations being completely alone, 1 very large cluster. Getting agreement between clustering measurements can be a challenge. For hierarchical clustering, we can measure something called entanglement. So entanglement is a measure of agreement for clustering dendrograms. The lower the entanglement, the better the alignment or the agreement between the 2 trees. So let's look at what this entanglement actually looks like, and that really explains, I think, the best why lower entanglement means agreement. So I'm going to save each of these clustering results as a dendrogram. I'm going to use a library in R called dend_extend, make a list of my 2 dendrograms, and then create what's called a tanglegram. So we'll actually calculate the entanglement. And this tanglegram really measures how often points are crossing over from one cluster to a different cluster. So we're looking at how often they are tangling. So low entanglement would mean that all of these lines would be roughly parallel. We would be seeing the same sort of patterns. High entanglement means that there's a lot of crossing over. Now, how many clusters should we keep? Remember, we might want to keep a small number of clusters for interpretability's sake, but certainly we want to explain as much variation as we can. So it's that bias variance trade-off and the simplicity trade-off as well. We can use within sums of squares to help us determine this. So this is just like a scree plot essentially for principal components was. Wherever this total within sum of squares starts to level off, that might be the number of clusters we choose to use. So maybe 6 clusters would be sufficient for the smiley. Now applying this to the public and private colleges, here are the hierarchical clusters for the public colleges. We see some pretty different patterns. We still have a group here, 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 and here, but hierarchical clustering resulted in one very large group of public universities. Now, can we compare hierarchical clustering to k-means clustering? Unfortunately, if we try to do that, the answer is going to be no. The reason for that is because we don't have a dendrogram representation of k-means clustering. We're not building it in that hierarchical structure, so there's no tree, so we can't really compare using entanglement. Now, how to compare the clusters? This is a little ad hoc. This is a little hacky. The cluster numbers aren't always the same, so that causes a problem for us. There also is no direct correspondence with the number of observations that will be in each cluster. So really the best bet we have is to visualize these. So here's what I'm going to do. I'm going to take that public data set. I'm going to add the clusters using k-means clustering to k-means. I'm going to create a variable with the clusters using hierarchical. So here we can see each of these. Now, cluster 1 using k-means might not be the same as cluster 1 using hierarchical clustering. So we want to look for how often observations are in similar clusters. So I'm going to summarize each of these, just how many fall into each of these pairs of clusterings. So cluster 1 using k-means clustering only occurs with cluster 1 using hierarchical clustering. So those are pretty linked. However, hierarchical clustering's cluster 1 has some observations in k-means 3 and some observations in k-means 4. K-means cluster 2 is split between 2, 3, and 4. It looks like it's closest to hierarchical 3. K-means 3 is pretty well split between hierarchical 1 and 2. K-means 4 looks like it's pretty similar to hierarchical 1. We can plot this just to see where these pairs are falling. So k-means clustering 1 only occurs with hierarchical 1, for example. We could also use a bar chart if you prefer to really see how each of these are split. Again, it's difficult to directly compare clustering results. So we will stop here with clustering. Again, as I mentioned, you'll have some problems on the homework assignment where you'll get a better feel for how clustering actually works. And you'll get to try this on some extra data sets. In the next video, we'll learn about deep learning and neural networks. Have a good day.